So now let's get to new stuff. Okay. So we are going to do approximate inference, and in the process we are going to introduce a very, very exciting concept that is not just restricted to Bayesian networks. It's now being used in a variety of scenarios, in game playing, in probabilistic planning, Markov decision processes. Actually, I have introduced this already in advanced in the lecture that we discussed for advanced satisfiability, and the idea is simulation, okay, sampling. But in satisfiability, we were sampling branches or something like that. This will be much more interesting. So, right, so sampling is the topic, and sampling is really awesome. Half of 20-30% of research papers use some kind of sampling today in AI literature. So this is just a very general and fantastic concept. But before we go there, let us start with the intuition. So the intuition, so to make intuition, so we have to compute probability using some kind of an approximate technique. That is the goal, right? We have to compute a complicated probability. We will worry about the complication later. But the starting point is, we want to be able to compute some probability. Okay? What is a common way to compute a probability in life? Experimentation and? You observe what's happening and then you see how many times what you were looking for appeared compared to the whole set. Okay, so that's the basic idea of computing any probability. We are not talking about Bayesian networks. It is count divided by the total count. Count of the event divided by total count of the event. So we have to remember this because this is going to be very important. So suppose I have a coin whose probability of heads is not known. What am I going to do? Flip it, flip it, flip it, keep flipping it, and after some time observe how many heads happened divided by the total number of times the coin was flipped. Will I ever get correct estimate? No. When will I get correct estimate? Exactly. So we should realize that even for this such a simple example, the only time we are going to get correct estimate is that when we have taken infinite samples. This is going to stay with us throughout the lecture.
Yeah, but you can get with it.
That's what I'm saying. So that's why we are talking about the approximations, right? So we can get pretty close quickly for this simple problem. But now this was learning a probability. We were not given a probability and we were trying to estimate it. It's a different problem. We will get there after this lecture. It's learning a Bayesian network. But even though Bayesian network inference is not a learning problem, the intuitions remain the same. We will generate samples. Now, if we were given a coin, we could flip it and we could get probabilities. Suppose I told you that I have a model of the coin. I will not give you the coin itself. I'm going to give you a model of the coin. You can ask the model to flip the coin for me and in simulation, and it gives me heads or tails. Does your solution change at all? You're just going to ask the model, give me a sample, give me a sample, give me a sample. What is Bayesian network? Bayesian network is a model for the world. Whether it's a good model, bad model, I'm not worried about that. But it's a model for what is really happening in some system somewhere. So, what we are going to do is that we are going to generate samples not from the world but from the model, that is from the Bayesian network. And because, okay, and then we will count. So this will be the high level idea. Now, a main issue with sampling anywhere, right, is the fact that the sampling should be unbiased. Samples should represent the world or the model that we are talking about. So suppose I wanted to compute the probability of people who are greater than 60 years of age who live in Seattle. Well, I could come to my class today and count how many of us are greater than 60 years of age. And hopefully, we will say, Seattle doesn't have people over 60 years. Is my computation wrong? No. What is wrong? My sample is not representative of the world. You could call people on a landline in the day at 2 o'clock, and then you might actually overestimate the number. Or you can call people on cell phone, in which case you might actually underestimate. Or you can just check Facebook. Let's check Facebook. How many of the people on Facebook are greater than 60 years of age and live in Seattle? I got my probability. So sampling is actually so common. We have been doing this forever in our life. We do exit polls, we do so many things, we do TV ratings. We always do sampling. We estimate some probabilities, essentially. But an unbiasedness in the sampling is absolutely essential for generating the correct probability distribution. However, in our class today, whatever sampling techniques we are going to see will be completely unbiased. So we don't have to worry about it, but we have to remember this, that whenever we have a sampling technique, the bias of the sampling is an important question that we need to think about. Yeah. Now, the best, one of the key characteristics of Bayesian networks is that it is something called a generative model. Now, it's a term, you don't have to worry about this term. It's a new term, it takes time to get this intuition, but the meaning of this generative model is that I can generate a data point in the world from the model. I can generate one full completely specified event by flipping coins. That is the meaning of a generative model. There are other models which are called discriminative models, which will not generate data for me but can tell me whether this is more likely or that is more likely, but will never be able to generate a full data point. Okay. We will not discuss discriminative models in our class, but if you have been exposed to something called conditional random fields, that's an example of a generative model. Sorry, discriminative model. But let's stick to Bayesian networks. So in Bayesian networks, we can generate samples from the prior joint distribution or from the joint distribution. How would we do this? How could we generate a sample? Suppose this is my network. I've added a radio or newscast. How could I generate some world from this?
What's random number? Is it an earthquake?
Exactly. Start from the top. Start from the root nodes. What is the probability that burglary is going to happen? I toss a coin and I figure out whether burglary happened or did not happen. Now I know the value of burglary. Similarly, I toss a coin and figure out earthquake happened or did not happen. Now I know the value of both burglary and earthquake. Now can I know what is the value of alarm? Yeah. Given this knowledge and given this conditional probability distribution, I toss another coin and figure out whether alarm went off or did not go off.
Does a coin or a weighted coin? Like
It's a weighted coin.
It's not a half coin. It's a coin that is flipped with the probability that is in the network. And you know how to flip such coins, right?
Yes.
Get a rand
Yes.
and get it between 0 and 1. And suppose my probability is 0.98 that I want to toss. Then if the number is between 0 and 0.98, then it is alarm went off. And if the number is between 0.98 and 1.0, then the alarm did not go off. Even if you have 3 or 5 such thing, you can just divide your 0 to 1 space in regions with that same probability distribution. You should think about this. Straightforward. So I will toss a coin for burglary, toss a coin for alarm, earthquake, then I can toss a coin for alarm and newscast, then I can toss a coin for call. And what would I get? I would get one sample. From which distribution? Exactly. I will get one sample from the full joint distribution represented by this Bayesian network. Now suppose I got 100,000 such samples and I want to compute the probability that there will be a call. What do? I see how many of those I sampled a call and then divide by the total number of samples and I got probability of the call. So computing marginal distribution, marginal probability is trivial.
Yeah, you're actually going to get with an epsilon for a nice. This is linear complexity.
Precisely. Now we have not talked about how much approximate it is, but essentially, if you have 10 minutes, generate samples for 9.99 minutes, 9.59 minutes, and in the last 1 second, just do a division and return the answer. Any questions on this?
Just my gut feeling is, isn't it just faster to calculate the probability instead of doing a simulation for this scenario?
Yeah, well, this is a very small network.
If you have small networks, then yes.
So even with 1,000 nodes, you would.
It depends on the largest factor. If you have some factors which there are too many edges are coming in, it will just blow up.
So In this methodology, you just have to go through the nodes.
Exactly, this is linear. One generation of one sample is linear in the number of nodes.
Computed is not related to the final independent of the, would we still generate that or?
It's a great question. So you are saying that to compute the probability of call, newscast is irrelevant. So if I knew that I'm going to generate probability of call, I want to compute probability of call, then I need not even generate probability of newscast. And you are absolutely right. You can say computation if you knew exactly what you're going to compute. Okay, but this is not interesting because this is marginal probabilities. So now let us see how do we compute conditional probabilities. But the idea is simple, idea is clear. I hope, right? Because if it is not, then it is only going to go deeper. Okay. Now here a call happened, excuse me, and I want to compute the probability that a burglary has happened. Okay, so it's a conditional probability that I want to compute. Let us do the very basic thing that comes to mind. The basic thing that comes to mind is that let me just still sample points as I was sampling. For example, I picked burglary, let's say burglary came out to be false. I picked earthquake, let's say earthquake came out to be true. I picked alarm, let's say alarm came out to be true. I picked call, let's say call came out to be true. I picked newscast, let's say newscast came out to be false. This is one data point. Okay. Let me generate another data point. Now suppose I computed lots of samples like this. Tell me if second sample is relevant to answering this question.
No.
I need each of you to get this. I know that call is true. That is given to me by my evidence. I want to compute the probability of burglary given call is true. I generated a sample in which call is false. Is this sample meaningful, relevant to my computation? What could I do?
No.
Just ignore it.
What happens if the probability of call is very, very, very low? You
Wait.
can run this for hours.
Don't run ahead of me.
Okay.
I'm building up to something. All your intuitions are right and we'll fix them. Not fix the intuition, but fix the algorithm. It is like this, I go to the university, stand in front of the hub and say, for all the people who are above 60 years of age, how many of them drive a BMW? So I stand there and I keep asking people, do you drive a BMW and are 60 years of age? Do you drive a BMW and are greater than 60 years of age? What happens? Very few people are greater than 60 years of age. So I stand there asking people, are you 60 years of age? Are you 60 years? And I get very few sample points because I am doing a lot of work, but most of these samples are irrelevant. This is called rejection sampling. Okay? So I reject the sample, and eventually I will have some set of samples which are live. I say the number of samples that lived, which have a certain value of the burglary, divided by the total number of samples that lived, is the probability that I wanted to estimate. This is accurate, but it is highly sample inefficient. So everybody with me that this is accurate? This will give me in asymptote, in the limit it will give me the right probability. In the limit of my sample.
Infinite time?
Given infinite time, it will give me the right probability estimates. You have a question?
Quick question.
Yeah.
Why is the number of live samples not the C equals C is true?
That's exactly. The samples that lived are the samples where C is true.
C is true, okay.
Okay, so far so good. This is called rejection sampling. The point is I'm sampling from still the prior distribution. Sampling from the joint distribution, but it's a prior distribution, not a distribution that does not take the evidence into account. It will return consistent posterior estimates. Posterior is the probability that I want to compute given my evidence. But it is hopelessly expensive, especially if the probability of evidence is low. Right? Standing in the middle of the university, looking for people greater than 60 years of age. There are some, but not the right place. And God forbid, I have many evidence variables, I am going to go crazy because because the probability of E will drop off really quickly as I have more evidence variables.
In the previous slide, I don't understand why you highlight some.
This is what happened in this particular sample.
The first one.
Yeah.
So, but -3 probability 0.03 is the probability being true.
It just shows which probability I'm going to use for flipping the
So
coin.
the first one.
So first one I use a 0.03 coin and I get not B. Then I get a 0.001 coin and I get earthquake. Then if I know that B is false, E is true, then I'm going to use a 0.4 coin to generate the alarm probability. And so. Okay. Now, yes, Harun.
The last statement.
You didn't understand. Suppose I knew that, suppose I wanted to estimate probability that this person drives a BMW. Given that they are greater than 60 years of age, they had their degree in Columbia University, and they live in Montlake Boulevard. So now I have given 3 evidence variables, that they have age greater than 60 years, they live in Montlake Boulevard, they got their degree from Columbia University. Now I'm standing at the university asking people, are you greater than 60 years of age? Oh, cool. Did you get your graduation from Columbia? Oh, damn. And go on doing this. So the point is that to find samples where a certain combination of evidence variables all comes together in exactly the way it is specified in the evidence will be very, very low probability if I'm just sampling from a prior distribution. Okay, so now I'm going to build towards this algorithm called likelihood weighting. Now it is clear to us that we do not want to sample by the prior distribution. We want to be able to sample based on the evidence that we have. So think of a rejection sampling as a 0-1. If you agree with evidence, it's full, it's 1. If you disagree with evidence, it's 0. Now we can't have disagreeing with the evidence. That is just wasteful computation. So we want each sample to agree with the evidence. But we will have to pay some penalty to agree with the evidence. So now each sample will not be 1 or 0, but each sample will have paid some penalty in order for it to agree with the evidence. And that penalty will be the weight of the sample. That's the intuition. Let me repeat this intuition because I see some of you are lost. I'm only giving you the intuition, not the algorithm. The intuition is, I want each sample to agree with the evidence. That's my requirement. If I'm only sampling from prior distribution, that is not guaranteed. So I have to change my sampling strategy. But since really the rejection sampling is doing the right thing, there will be samples which will want to not agree with the evidence. I will have to push them towards agreeing with the evidence. The amount of push I have to give for a sample to agree with the evidence will be the weight of that sample. If I have to give more push, the weight will keep reducing. That's the intuition. So now I'm going to sample my points. Each sample will have a weight.
So, still like if you do the previous way, like just do random samples and like for the non-live ones you assign a weight, like how far it is in some sense from the...
No, that won't help because once I assign a certain value to a parent, then the later probability flips depend on that value.
So how do you start?
Yeah, so we are getting to likelihood weighting. So the idea, as I said, is each sample has to agree with evidence. You have to pay some price for the agreement. The algorithm is as follows. It's actually a very simple algorithm. You fix the evidence variables, never sample them. Sample only the non-evidence variables. Weight each sample by the likelihood of evidence. What does that mean? Let's run through the example. So suppose I know that call is true. I want to estimate probability of burglary. Same thing. So I start my sampling process. I generate burglary as before. I'm not paying any price. So far so good. Generate earthquake as before, not paying any price. Generate alarm as before, not paying any price. Now comes the point. Now I'm about to sample call. Do I want to sample it? No, I know it, what the value is. So I don't want to sample it. But because I am not sampling it, I will be paying some price. And because alarm is true here, the price that I will be paying is 0.8. Alarm is true, I want call to be true, that happens with probability 0.8. So my weight here would be 0.8. Intuitively what happened? If I did not do this, then
If you had sampled C, you would have gotten C true 0.8 of the time.
0.8% of the time, like 80% of the time, precisely. You got the intuition right. If I had sampled C, I would have gotten C 80% of the time. That is my weight. Similarly, here the weight is 0.05 because alarm is false, and I am sampling C to be true, forcing it to be true. That is 0.0. And now my probability formula is weight of the samples, sum of weights of the samples which have burglary to be true divided by total weight of the sample. So I take to the weighted average. This is the algorithm. Now I'm going to do my best to give you the proof that it works. But I will make sure that I don't spend more than 5 minutes. Yes?
So how does it work when you have two or more?
You multiply the weights.
Or you keep multiplying?
Yeah, great question. So if you have two evidence variables, then I just keep multiplying the weights. As many times I force my sample onto a certain value of a variable, I just multiply it. Which makes sense, right? Because that's what would have happened if I was just flipping it. Okay. It's actually a pretty good algorithm. It's a fine algorithm. Much more sample efficient than rejection sampling, obviously. In order to prove that this is giving me the correct estimates, I have to show that the samples probability, sampling probability multiplied by the weight is same as the prior probability. So I have some probability with which I made a certain sample. Now this is not the prior probability anymore, right? Because I'm forcing some values. So what I want to show is that this sample would have happened in the rejection sampling case. This sample multiplied by this weight is the same probability of generating the sample as in rejection sampling. So let's think about this. So what is my sampling probability for likelihood weighting? It is probability of non-evidence variables given their parents, because I am not using this probability for evidence variables. What is my weight? My weight is probability of evidence variables given the parents. If I multiply the sampling probability and the evidence probability, what do I get? I get the prior probability. This is exactly the semantics of Bayesian networks. I get the joint probability distribution. So essentially what I have shown is that the sampling probability times the weight is the original joint probability distribution. So in some sense I am sampling, if I multiply with the weight, I am still sampling like I was doing in rejection sampling, but I am not generating explicitly any samples which are not agreeing with the evidence. So therefore these probability estimates are accurate. I won't spend more time than this on this. Some of you got the intuition, others should get the intuition by reading the book, others should take my word that this is returning consistent estimate. Now, this is a better algorithm. It is obvious, right? Than rejection sampling. Why is it better?
Good information from
Because I'm not wasting so many samples, I'm not throwing away samples. When might it have a problem also?
Of getting a sample of whatever we have observed, getting that T0. We cannot end up in that state.
Zero probabilities are a problem for Bayesian networks in general. Let's avoid zero probabilities yet. We'll talk about zeros, which are hard. But even otherwise, so here's the intuition. See, in which order am I sampling? Topological order, parent, child, 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 child. Suppose my evidence variables was way up at the top. It's pretty good because I generated the evidence soon, and then all the next probability distributions will depend on the value of the evidence variables. Right? That's pretty good. If, however, my evidence variable was at the bottom, then I did all the work without thinking about evidence and then set my evidence variable to be whatever value we required.
the general case.
I don't see why that a problem.
That is a problem because my evidence variable is not biasing my sampling. I am sampling variables completely a priori, and I may end up with a really low weight for the sample.
I see.
But it might happen that there are situations where, given the evidence, there is high weight possible, but then I have to sample the parents in a slightly different order. So, major problem with likelihood weighting is that in practice what happens is that a few samples end up happening nearly all of the total weight, sometimes at least. And more importantly, late occurring evidence variables. The evidence variables that occur late in the Bayesian networks are not guiding sample generation, and so they have very low weight. So they are not rejected like rejection sampling, but they are still not contributing much to what we want to contribute. So to fix this problem, we will do the final algorithm for an inference called Markov chain Monte Carlo. Actually, Markov chain Monte Carlo is a general name for a set of algorithms. We will do one of those called Gibbs Sampling. So, we did lots of algorithms, exact algorithms, approximation algorithms. If you have to retain one algorithm from this full discussion, it has to be the one that comes last. Therefore, it's Gibbs Sampling. Okay? Let us first go through the algorithm. The algorithm does the following. It first of all fixes all the evidence variables. Obviously, evidence variables we never want to sample or anything like that, so we're going to fix them. Then we're going to set values of all the other variables randomly. Okay?
Uniformly randomly or
Any random, it doesn't matter.
pick something?
It really doesn't matter. Yeah, uniformly. This is almost like local search, right? Remember, we just started from some point and wanted to hill climb. Of course, we can't hill climb like that anymore because we want to generate probabilities as opposed to reach a point. But the intuition is this. We're going to perform random walk in a neighborhood space. A neighborhood space of complete variable assignments. Again, local search, nothing different. Think, satisfiability, greedy sat or walk sat kind of algorithms. We'll pick a variable x and we are going to flip it. But we will flip it based on every other variable. So assume that I know everything about my world, and I am saying suppose everything else remained the same and I could resample one variable, what would I do? Well, I will resample it with the probability of that variable given all other variables. There's a different question of whether we can do this efficiently, and I'll show you that we can. But let us suppose we can't do this. I got a new variable, new value for x.
You do it once or you do it for a while?
Wait. I got a new variable for x that becomes my new variable, world. I repeat many times. I keep doing this, and what I get is a set of samples. Hold your questions. And then I just use my averaging trick or denominator trick. I look at for how many times b was true, and divide by the total number of samples, and I got my probabilities. Sounds like magic almost. You can prove, and I won't, to spare you. You can prove that this will converge to the true probability distribution. The intuition of the proof has to do with the fact that this flipping one variable and going forward in time is like a Markov chain. You guys have heard about Markov chains? Are you serious?
Sorry.
Wow. Okay. Go read about it. It makes a Markov chain, and if you remember your Markov chains, then many Markov chains have something called a stationary or steady state distribution. And you can prove that under some conditions, starting at any random point, given enough time, keep flipping, given enough time, your Markov chain or your chain of samples will reach a steady state distribution that is given by the posterior probability of posterior joint distribution. In other words, simply put, you do this for long enough, you will start getting samples from the posterior distribution that you wanted to get samples from right in the beginning, and then you can simply do your division. However, this is very local, right? We're changing only one variable at a time. So what might happen is that your initial starting point and your initial few estimates, few samples will not be from a true posterior distribution. So you have to wait some time. So you generate samples, generate samples, generate samples. You keep doing this, and at some point you say, most likely my Markov chain has now reached its steady state distribution. Then you start counting your samples from that point forward. So this is called mixing time or burn-in time. That you start your Markov chain from some random position and you just let many samples go away, like 1,000 samples, 10,000 samples. You just forget them, let them go. And then you say, okay, now my Markov chain is giving me the correct distribution. Now let me sample and then I do my average. In fact, people in practice don't take every next sample. They take, say, every 50th sample or every 100th sample. See, computers can generate these samples very fast. It doesn't matter. So in practice, what they do, wait some time, let the Markov chain mix, then take every, say, 50th or 100th sample and then memorize these samples and then compute your probability from this set of samples. In my opinion, Gibbs sampling is the easiest algorithm to implement, which has the good theoretical properties as well as it's sample efficient.
Can you take every 50 or?
No, so it has settled, but because it is doing only local moves, it's a good idea to take a sample after every step because you may have to take lots of samples. So yeah, I'm not 100% sure, but that's how practitioners do it. There's also a lot of theory behind how can I detect that my Markov chain has mixed, how can I detect that it is not, but we won't get into the theory. I don't even know about it.
So every step one, it just picks the bolts around.
I just didn't know it is one variable is fused. Now, I still have to talk about how to compute probability of x given true is equal to true given all other variables. Is it that hard? I know there's a lot of variables, given all the variables, but are all the variables relevant to x? If I know all variables, I also know its Markov blanket. If I know its Markov blanket, do other variables matter? So it is every variable is conditionally independent of all variables given its Markov blanket. So therefore, probability of x given all other variables is equal to probability of x given its Markov blanket. Okay. And in fact, you can just remember this formula, although we can prove it also, that it is equal to alpha times x, that variable given its parents, times product of for each children, that variable given its parents. Okay. Let's take an example. Suppose this is my Bayesian network. The variable that I want to flip is x. This is my Markov blanket, A, B, and C. So I want to really compute x given A, B, C. Using Bayes rule, it's no, not Bayes rule. Using definition of conditional probability is x ABC given divided by ABC. X ABC is A, x given A, C, B given x comma C. You guys know how to write these equations now. Now notice, PABC, PA and PC are all constants as far as different values of x are concerned. So they can just be called alpha. We like to call these things alpha. So now what is left? X given A and B given x comma C, which is exactly what I had said, probability of x given its parents, and for each child probability of that node given its parents. So probability of the child given its parents and probability of the node given its parents. And then you can renormalize this. That's it. So you can take an example if you want. This is a simple Bayesian network. It says smoking leads to heart disease, lung disease, shortness of breath. And let's say I know that somebody smokes, that they have shortness of breath. I want to figure out whether they have a heart disease or lung disease. So I start with, I randomly sample H and B, randomly set H and B. So let's say I know that they have heart disease and they have lung disease. Then I compute the probability of heart disease given all other variables. All other variables actually will be all four because this is parent, this is child, this is the other child of the parent, other parent of the child. So I'm going to compute this. And I do. I get some probability. I flip a coin from that probability. Suppose I say the person does not have heart disease. So I move to this state now where S is true, B is true. There is no, it doesn't have a heart disease, have a lung disease. Now I go and resample lung. So suppose the result is, G, then I get a new sample and I keep doing this. So keep doing this and I get my samples from the Markov chain. So this is the summary. No samples are discarded. There is no problem with samples of low weight because I am generating each sample given its Markov blanket. So I am using the evidence in generating these samples. Can be implemented very efficiently. This is old numbers. I'm sure we can now generate more than 10,000 samples a second. There are disadvantages, but I think we can sort of skip a little bit now. But the disadvantage is what happens if the relationship between two variables is deterministic. Suppose I say y equal to x. So initially, let's suppose I pick x equal to true. Then how will I pick y? True. If y is true, how will I pick x? True. So it will keep going between true, 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 true. But there is another possibility which is false, false. But Gibbs sampling will never pick. So Gibbs sampling says that all probabilities need to be greater than 0 or less than 1 in order for Gibbs sampling to work. But still, if the probabilities are really small, some condition probabilities, then Gibbs sampling still has problems. So in our department, there's an algorithm by Pedro Domingos called MCSAT, which is Markov chain satisfiability. So the part that is deterministic is solved by satisfiability solvers, and the part that is probabilistic is solved by Markov chain techniques. It's pretty awesome, and there are other techniques to handle really small or really large probabilities in the probability distributions. We will not worry about it now. So that is the summary of Gibbs sampling. I have to generate each sample given its evidence, and then finally take the total number of samples and number of samples which have certain variable that we were looking for, and that gives me the probability. Yes,
When
Ramesh?
you say randomly set, you actually set it with the probability?
No, just random.
So in this case, you knew S.
S and B we won't set, but H and B,
No,
H
so
and
when you want to set heart disease, we knew H actually, so should we set it using 0.6 probability or just?
see, the
absolute?
setting happens only at the first step. It's like the random initial starting points, right, in a local cell. So I randomly set them, doesn't matter where I start from. Right. Then I'm generating the samples using the Markov blanket sample. So that is not setting, that is resampling. So then you are using the probability distributions. There are many other algorithms. You can take a full course on probabilistic inference called probabilistic graphical models. It is taught every year in this department. It is being taught this year, I think, also this quarter. It's an advanced course. It's a full field. There you will learn about other exact inference techniques called junction trees, many other approximate inference techniques like belief propagation, variational methods, and Metropolis Hastings, another algorithm which is better than Gibbs sampling, and the other techniques for Markov chain Monte Carlo. We will not worry about.